Here the biomass is burning, and biomass composition is given as this formula here. This formula is given in the form of a generic formula, which is CuHVOWNXSY, which is for every U molecules of carbon there are V molecules of hydrogen, or V atoms of hydrogen, W atoms of oxygen. And when we burn this material here, we would be needing U moles of oxygen. For every one carbon, we need 1 mole of oxygen to turn it into CO2. Same way, when we have V moles of atomic oxygen, it requires 1/4 or half mole of oxygen to combine, or V over 4 moles of oxygen to combine it into VH2O, V over 2 half H2O. Now, we can do this stoichiometry for all these elements here, all these, meaning sulfur also burns and forms sulfur dioxide. So S plus O2 goes to SO2. So 1 mole of sulfur requires 1 mole of oxygen. So Y moles requires Y moles. You can see that here, Y moles. Okay. Same way, 1 mole of carbon requires 1 mole of oxygen. So U moles of carbon, which is there in the biomass here, will require U moles of oxygen. Hydrogen is 1/4. So that's what we have from stoichiometry over here. If you look at so you need V over 4. However, there is a negative sign for W, which means there is already oxygen built into the molecule here or inside the fuel, so we need to reduce that. So how many moles are available? Since there are W atoms here, W over 2 is the number of molecules that are available, and you subtract that from here. So that gives us the number of moles of oxygen required. So this is the number, U plus V over 4 minus W over 2 plus Y. Excuse me. But this oxygen comes along with it. Every molecule of oxygen comes with it 3.76 molecules of nitrogen, or every mole of nitrogen brings along with it 3.76 moles of nitrogen. So that is also added here. So this is the number of molecules or moles of air that will be coming into the process. So following this, actually, if you calculate here air to fuel ratio down below, you can see that very clearly here. 4.76. So every mole of oxygen brings along with it 3.76 nitrogen. Together, it'll be 4.76. So 4.76 moles come for every mole of oxygen, air. So how much air? U plus W over 2, which is all over here. U plus V over 4 minus W over 2 plus Y is the number of moles required for 1 mole of biomass with this composition over here. Okay, that is 1 mole of fuel. Okay, this is the number of moles. So this is moles of air per mole of fuel. But mole of fuel, when you multiply by the molecular weight here in the denominator, you will get the mass of fuel. And air, number of moles of air multiplied by molecular weight of air will give us the mass of air. So this will give us air mass divided by fuel mass. So let's take a look at this a little bit here. So I'm going to actually do a simple problem here, and then we can figure this out actually. So let's do this. Okay, so I'm going to go to okay, so if we have a biomass with a composition, for example, carbon here, let's see here, carbon C, and we have here, I can write this here, C H 1.8 O 0.57 and nitrogen 0.01. Sulfur would be very little, actually, sulfur. That'll be, let's say we have 0.003 sulfur, and this one would actually, this is the molecule of biomass. When this burns with enough air, the amount of air that will be required is, according to our formula, air required to fuel will be 4.76 times, right? U happens to be the coefficient or number of moles of carbon, which is 1 here, and then oxygen, which and then the hydrogen requirement is V over 4, which is 1.8 over 4, and then minus, which is here the W, which is the oxygen. So there is built-in oxygen, so we need to subtract that here too. And then we need to add whatever is required for sulfur. So let's add for the sulfur 0.003. All right, this many moles of air are required for 1 mole of fuel, biomass. Now, always remember, if we have to convert moles into mass, you need to multiply by molecular weight. So now we multiply this by molecular weight of air, which is 28.84. On an average, sometimes you can take it as 29. It's not going to make much of a difference. And molecular weight of fuel, again, that is a kind of an unknown here. So we need to figure that out here, molecular weight of fuel. So in this molecule of fuel, we have 1 carbon atom. 1 carbon atom is 12 atomic weight, and there are 1.8 atoms of hydrogen, so 1.8 times 1 atomic weight of hydrogen, plus plus there is oxygen in here, which is 0.57 atoms of oxygen times 16, plus there is 0.01 nitrogen times 14, all right, and then plus 0.003 times 32. So this will give us the molecular weight of fuel. So that happens to be, in this case, 22.56 roughly. Okay, so now if we multiply this molecular weight of fuel by 22.56, okay, this is molecular weight of air, this is molecular weight of air, and this is molecular weight of fuel. So now what we get is here, total will be air to fuel ratio, which is grams of oxygen. This, if you do the math here, it comes out to be 6.45. So this is the air to fuel ratio. In other words, 6.45 grams of air are required per gram of fuel. in this case biomass, or it is the same thing, 6.45 pounds of air per pound of fuel, or 6.45 kilograms of air per kilogram of fuel. So that is the reason we call it air to fuel ratio. This is a ratio. This 6.45 is the ratio. So for every unit mass of fuel, you need 6.45 units of air. So that's how we determine air to fuel ratio. I hope now this is clear.